tell you what is the minimum total stress at that location. So the lines are a model, the dot is field information. Not only we know the pressure for a hydraulic fracture to start propagating, the absolute minimum, but also we know the relative magnitude of stresses in this case. We know that according to this plot, at the location, for example, this depth C, the minimum stress is horizontal. And I actually don't know in which direction it is, but actually I do know. This place is in a formation called Vaca Muerta in Argentina. If this is South America, and this is Argentina, somewhere, something like that. This place is somewhere over here. And this is the north, this is the east, and this is Uruguay, and this is Brazil, and this is Paraguay. Okay, something like that.
Is horizontal minimum stress north-south?
So, in which direction is the minimum horizontal stress?
North-south.
Why?
Don't you have the oceanic plate coming in, converging in an east-west direction?
Yes. So, I want to repeat what Stephanie said. Here, at this location, we have the Pacific plate getting subducted with the South American plate. And that makes this part to have a lot of mountains. Those are basically the Andes. They continue all over South America, but make at this location have the horizontal stress higher in this direction, east-west, than in direction north-south, because of this tectonic compression. Because of that reason, let's make then now this drawing more accurate. Now I'm going to do it in 3D over here. This is going to be the north, this is going to be the east, and this is going to be the axis D. That stands D for depth. Okay, so that one is going down. So if that's the case, then let me change this. The minimum horizontal stress is going to be in this direction. And actually, I have some colors, so probably I can do it in colors too. Green, that's SH mean, and SH max is in blue, and it's going to go in direction east-west. And what is going to be the third one?
SV.
It's going to be SV, and it's the intermediate stress because it's in between the lowest and the maximum. And this is going to be SV. So this is what you're seeing in this plot. And our objective for this first part of the class or part of the program is going to be to understand what these stressors are, to understand what is the mathematical way that we can express this stress, and to calculate something which are called invariants of the stress tensor. They're going to help us understand a little bit more about, instead of doing this complicated plot of a cube with 3 stresses, just to plot just 1 or 2 quantities. So you're going to see that here you already have a list of things that you're going to have to do related to compute what is the stress gradient and to write some of those stresses as matrices, and then to calculate what are called the invariants of the tensor, and also to plot some of those stresses, either as more circles or also as just plotting the invariants. And although we do not have the tools yet to calculate the horizontal stresses, we do have the tools to calculate vertical stress. That's an easy one. And actually it's the most reliable quantity that we can get out of the subsurface. And for that, that's going to be the second problem. I'm going to give you an LAS file and a well deviation file. And based on those two, you're going to tell me what is the vertical stress. So we're going to get to that later on, but that's the objective for this first week. First, to calculate vertical stress, and second, to understand stresses and to plot stresses with different type of metrics or different kinds of plots. Okay? Yes?
Yeah, so two questions.
Yes.
So the first one is, are we basically set the dot from the measurement as the ground truth, and we don't dot it?
I don't think we know depth, right?
All right. So we do not know the absolute depth, but we do know the value of stress. We do have numerical values. For example, in this track, this is 6,000 and this is 12,000. So I know, for example, that at this particular depth over here, let's go. Let's try to complete this. This is 6,000, this is 12,000, and there are 1, 2, 3, 4, 5 grid spaces. Then what is going to be the next number? 7,200. The next one is going to be 84. The next one is going to be 96. And the next one is going to be 10,800. And I know, for example, that, let me follow this one, is easy. This depth right here, I know that the vertical stress is 9,600 psi. I know some of you guys know this already, okay? And some of you don't. But the objective is for this first week that everyone will know this is very easy. What do you think is the depth at this place? You know the vertical stress. The question is what's the depth? More or less. I'm not asking you for a very accurate value. I'm asking you for some approximate value. And as I told you already, this is right here on the continental shelf, and this is onshore.
9,600 feet.
Why? Why do you say that, Jack?
Normally it's 1 psi per foot for overburden stress.
The gradient of overburden or total vertical stress for typical rocks is about 1 psi per foot. So we know that if the place is at 9,600 psi of vertical stress, the depth is going to be very likely around the 9,000 to 10,000 feet of depth. How many kilometers is that? Guys, I'm going to ask you to deal with psi and also with metric units, okay?
60 megapascal.
Okay, but in terms of depth,
3,000.
about 3 kilometers, right? 3 kilometers of depth. How many miles?
5.
like 2 miles more or less, right? So that's the depth. I hope that by the end of the class you're going to be very comfortable with MPAs and with PSIs and also with in terms of depth. All right. So for the assignment related to your question, I'm going to ask you to believe these trends, what these lines predict as a horizontal stress.
I would ask about the right dot. You said something about the right dot from the
from the field.
From the field.
Yeah.
Do we take that as the one truth, so to speak, because it's not?
Well, in this case, this particular line was calibrated so that the line will coincide with the dot. It may not match exactly everywhere. Here, it looks like it's right on top of it. But here, a little bit, more or less, and here as well, but not exactly. But this model was developed in a way that was calibrated so that the model will match the measurements from the field. Yes. Well, I mean, you develop a model, and within that model, you have some variables.
Okay.
And those variables are the ones that you adjust to make the model match what you see over here. In this case, what it was matched is related to this part, and is what is called a tectonic strain, which is how much the rocks deform at that location due to tectonic forces. Yes?
Just an annoying question. So we said we have vertical stress due to the overburden,
Yes.
and then we have 2 horizontal stresses.
Yes.
I would just assume these horizontal stresses are perpendicular to each other. Or
So we're going to see some of these if the vertical stress is a principal stress, and we're going to see what that is in a bit. The other 2 are also principal stresses, and they are perpendicular to each other. That's going to be the case.
is it true for everywhere? Or
Yes, in terms of principal stresses, yes. Yes. You have a question, Viti?
So depth D is the depth peak, and also depth E is also the peak over the bottom of the graph, right?
SV?
No, the depth D, depth
Depth D, yes.
that one on the graph.
Yeah, this is depth here.
No, I mean on the graph.
Down here.
Like you point out the.
Oh, yes.
So those are you show that the peak is the depth E, and at the top.
No, but I mean the depth E is this depth over
Yeah,
here,
that depth, right?
that level.
Okay, and the depth D is at the peak.
It's a particular point. In the assignment, for example, you will see that I'm asking you
Oh yeah, because
to,
of the resin.
to tell me what is the state of stress at locations or at depths A, B, C, D, and E.
Yeah, because.
So you have to get from this plot what are the stresses at those points.
Yeah, so that's you pick the peak. Pick the peak of the.
At each depth,
Yeah.
you're going to have 4 values: pore pressure,
Yeah.
SH min, SV, SH max. Okay, so now that we know in which direction we're going, let's start talking about the tools that we're going to need in order to deal with these problems in a quantitative manner. All right, so the first thing that we're going to do is to understand what stress is. Let's say that you're interested in a particular location at a particular depth, and that you drill a wellbore to this location, and you want to know at that depth what is the state of stress. At this particular depth, for example, you could have a pore pressure, or you could have a temperature. How many numbers you need to define a pore pressure? How many numbers? It looks like a tricky question, but it has some meaning. So if I ask you for temperature, let's do temperature. What a typical temperature may be, for example, I don't know, 100 degrees C. So it's just one number, okay? And the same with pore pressure. Pore pressure may be, for example, 8,000 psi. It's just one number. And in math, that's called like in scalar. It's something that does not depend on the coordinate system. I can have this coordinate system in any place. It can be rotated in any orientation, and the number is going to be the same. Always 100C is going to be 100C. Always 8,000 psi is going to be 8,000 psi. It doesn't depend on the coordinate system. Let's say that in this particular location that we did the fracture over there, we are draining fluids so they get into the fracture. And this is the vector of velocity v of a fluid moving from this location to that location and finally into the fracture. How many numbers do I need to define that velocity vector in 3 dimensions? 3 numbers. I need 3 numbers because I'm in 3 dimensions. In this particular case, for example, this is a v. The vector v maybe it doesn't look it's going in direction 1. It doesn't look it's going in direction 3. It looks like it's going mostly in direction 2, right? So I could say, for example, 0, 0.1, 0 feet per second. And now I need 3 numbers. That's a vector, okay? Can you give me another example of a vector?